Welcome to Astronomy 103. I'm Michelle Cullen, and this video is about Planet Designer, a tutorial on how to be successful on this week's lab. Open up your Blackboard program and download the lab. You're going to find a link to the LASPC interactive program, Calvin Klein Planet Designer. In order to use this program, enable Flash Player and then drag your planet along the dotted line and change the distance from your planet to the sun. Some concepts that will help you be successful in the lab are the terms of astronomical unit. You may be familiar with the AU. It is just simply one Earth distance to the sun, and it's 150 million kilometers, but it's much simpler to compare all of our planets to this distance. We're going to also compare the mass of the planet in terms of Earth mass and also the radius in terms of Earth radii. You'll also be able to change the little blue triangle sliders that will change the mass and hence the density of the Earth as the volume changes as well. So you'll see all of these different variables located in the 4 windows. As you change these variables, you'll notice that the temperature changes as well. And in astronomy, we use the temperature scale of Kelvin. It's simply noted by capital K. Just a chart here to compare Fahrenheit and Celsius. You'll see that it's a simple conversion. You add 273 degrees to the Celsius and you'll get your temperature of your planet in Kelvin. You can also notice that Kelvin is something that's used on your light bulbs. When you go to Home Depot, you can see that a lower temperature light bulb is more red and a higher temperature in Kelvin is more blue, which is more energetic and hot. As you progress in your Planet Designer app, you'll move next to the concept of albedo. And albedo is simply the reflectivity of different colors. How much energy of the sun can be absorbed and converted into heat. So you'll play with the tools on the left menu and you can see that you can color and change your planet any color or combination you want. And as you do that, you'll see that the different percentage of albedo will change. It will be a number you can record in your lab. Your albedo of your planet will be given as a percentage, and if we look at the albedo of Earth, the average is 30%. However, different surfaces like the Arctic, where you have lots of white snow with the high reflectivity of an albedo of 0.9 or 90%, and then you'll have dark areas that are black, and those have a low albedo of like 0.10 or 0.1. I highly recommend you go to this NASA video that shows the changing sea ice minimum, the recording every summer when the sea ice is at its lowest. And you can see it over from 1979 to up to 2019. And it's quite remarkable of how our sea ice is diminishing in the last. The next section in the program looks at how the atmospheric pressure of a planet can work to change the temperature. Now, the sheer thickness of the amount of volume of gases in the atmosphere act as a greenhouse effect. And we measure that atmospheric pressure in the barometer. So 1 bar is in terms of pressure per square unit area, and in English we use pounds per square inch. In the metric we use kilograms per meter cubed, and you can see here that the tire pressure puts more air into a volume, and so it has a higher pressure. And that's the same thing too. When you have more air in your atmosphere, gravity is going to pull it down and it will have more pressure. The pressure also decreases as you go up in the mountains and you go higher and higher. You have less air per cubic meter. Now in the app, you'll be able to slide the sheer thickness of the atmosphere on the top bar, and then on the bottom you can actually change the type of greenhouse gas. This graph shows a comparison of close by planets Venus and Mars. The graph on the left shows a comparison of Earth, which has a blue line, and we see that at the surface of the Earth, where we're at 10 to the 0, we're at sea level, we have 1 bar of pressure. And as we go up in the altitude, we follow that graph back to the left, our pressure decreases as we go up in altitude. Now on Venus, it's interesting. We start on the sea level at the bottom right at 92 bars. It has much more carbon dioxide and a lot more volume, gas per unit area of carbon dioxide than Earth does. So that's why it has the pressure. Now as we go up, we can see that when we get to a certain point, we can actually get to 1 bar of pressure, and that is about 60 kilometers up. And so there's a place where you could float in a balloon on the clouds of Venus, and you would be at the same atmospheric pressure that we are used to here on Earth. If we look at the atmosphere of Mars on the right, we can see that we don't even use the same scale. We use millibars instead of bars because there's just so few atoms of different gases of carbon dioxide per unit area. Like on the bottom, you can see here we have 1,000 grams of gases. The gas actually has a weight per meter, and on Earth that is compared to Mars with 3 grams. A simple review of the greenhouse process. It's where visible light is able to penetrate the atmosphere and gases. It hits the surface and is radiated back as infrared. And the infrared is trapped in the gases like clouds and water vapor, carbon dioxide, and keeps the heat in. I also want to tell you that not all greenhouse gases are equal. The main ones on Earth are water vapor, which is not on this chart, carbon dioxide, and methane. And we look at some of the other greenhouse gases. Those other ones can be much more potent, having an individual molecule 1,000 times more greenhouse effect than a molecule of carbon dioxide. The next stage in the Planet Designer application is a summary, and you'll get to see what your planet looks like. You'll design 2 different planets with different parameters, and you'll get to see if they are able to have liquid water on their surface. The last concept of this lab is under EM radiation, and you'll see that you'll learn about how different stars radiate in different intensities of their peak intensity. A cooler star is going to radiate in more red wavelengths of visible light, and it will have longer wavelengths. And a hotter star will have everything pushed to a hotter, more energetic blue wavelength. This can be summarized by Wien's law, and it allows us to solve for the temperature given the peak wavelength of an object, known as lambda max. So we can see that everything radiates some form of infrared radiation because light is not only visible light, it's actually the invisible as well. In astronomy, we use the concept of a black body, and that is if you heat an object up hot enough so that it is radiating in all wavelengths of light. That means that it's radiating and glowing in the visible light that our eyes are adapted to see, but it's also glowing in infrared, radio, ultraviolet, X-ray, etc. Just like our star is glowing in all of those wavelengths. And everything that is alive and that has molecules that are moving actually is emitting some sort of electromagnetic radiation. So that means you are actually glowing in infrared. If we look to the left, we can see the visible spectrum, and it has the rainbow colors being separated by a prism. And you can look at the wavelength, the distance from the top of the crest to the other, and you can see that the red wavelengths on the bottom are longer than the more energetic blue wavelengths on the top. And it turns out that according to Wien's law, we can see that this change in energy will affect the temperature of an object. If you want to play with this concept more of the peak wavelength of a star and its temperature, you can go to another application in this link here, which is the University of Colorado at Boulder, the PHET, the PhET black body radiation curve. And it will enable you to change the temperature of the sun on the right to a different star, and you'll see how the spectrum switches. If you go up to the top to the very bright star and hot star Sirius, you'll see that the wavelength shifts to the left. Now this lab will show you what temperature your planet is and also what radiation or wavelength it's glowing in. And if it's glowing in visible light, it will be on fire, it will be a star. If it's glowing in a lower energy, it will most likely be in infrared. And if you had an infrared camera, you could take a picture of it. Just like in this image above, you can see a person glowing in infrared. Well, now that you're familiar with the program, go through your lab and go through and fill out the data and then do a great lab write-up. You'll want to follow all of the directions on our standard lab report, and at the very end when you're done, do your abstract. Make a clean, crisp, and a postage stamp image of what you did in this lab.